So this lesson is intended to be a recap lesson as opposed to teaching you about something from the very beginning. It's intended to recap integration by substitution, and this should be really a revision video more than an instructional video, as I've said. So in this example, we can see that we don't have a function which is the differential next to it in terms of this x and this value or this expression here. So what we're going to do, we can't really work with something to the power of a half times by x. That's going to be really difficult to expand and be able to integrate. We can't do it in each separate section, so we're going to make a substitution. And in this case, what we're going to make a substitution for is u squared, and that is going to represent 2x plus 5. So were I to rearrange that, I would get that u is equal to the square root of 2x plus 5, which I'm going to write as a half, because the next thing I'm going to do is differentiate that and get du by dx. So this is the basic, guys, and most integration by substitution questions. You start with a function, you differentiate it, and we substitute all the different parts. So if I differentiate inside my function, applying the chain rule here, I'm going to get 2. Then if I consider the power, bring that down to the front, so I'm going to get a half, 2x plus 5, and that will then become to the power of minus a half. So du by dx is equal to, 2x plus 5 to the power of minus a half there. There doesn't seem to be anything that we can really sort of easily substitute here, so I'm going to need to do a little bit of work to make sure that I've got something that I can substitute so that I end up with all u's and a du at the end. So if I rearrange this a little bit, du by dx is equal to 1 over this 2x plus 5 to the power of a half. And I know from earlier on, so up here, that 2x plus 5 to the power of a half is the same as u. So du by dx is equal to 1 over u. So then rearranging that, I can get here that u du is equal to dx. So let's substitute in the bits that we have got so far. So I don't really have an expression for x yet. I do know that the square root of 2x plus 5, which is the same as 2x plus 5 to the power of a half, is equivalent to u. And I do know that I can replace my dx here for u du. So u du. So the only thing really I've got left to concern myself with is this x. So if I continue to think about what I've got on the side here, just a minute because I need a little bit of room. So on the side here, I am going to go back to the beginning. So if u squared is equal to 2x plus 5, u squared minus 5 is equal to 2x. So u squared minus 5 all over 2 is equal to x. So that's what I'm going to substitute in for my x here. So I've got u squared minus 5 all over 2. These bits here give me a u squared and a du. I can now perform that integration once I've expanded the brackets. So I'm going to integrate u to the power of 4 over 2, take away 5u squared over 2. Because they've got that common denominator of 2, I am able to sort of write them as separate terms here. If I had something on the denominator like 2 plus x, I wouldn't be able to do this. So integrating that, increase the power by 1 and divide by the new power. But obviously I had a 2 there to start with, so we're going to be multiplying that by 5 now. Take away 5, again, increase the power by 1, divide by the new power. And then never, ever, ever forgetting that plus c, because my integral has no limits. So I'm going to get u to the power of 5 over 10, take away 5u cubed over 6 plus c. Lovely. That almost looks as though we finished, but remembering the original question had an x in it, so we're going to want to put that x back in. So let's go and just remind ourselves of the substitution that we made. So the substitution that we made was that u squared is equal to 2x plus 5. Okay, so if I want to substitute for u, I'm going to be substituting in there 2x plus 5 to that power of a half. So in the first part, I'll have 2x plus 5 to the power of a half, all to the power of kind of 5 there. And then 5u, so the 2x plus 5 to the power of a half, and that's all kind of to the power of 3 there, plus c. So I'm going to get 2x plus 5 all to the power of 5 over 2 all over 10. Take away 2x plus 5 all to the power of 5 over 3 all over 6 plus c. And there we have the final answer. One thing that I wanted to mention here is that with the majority of the questions given in an exam, you are usually given a sort of a value to work with here. So in this example, you'd normally be given the instruction that you're going to let u equal 1 plus sine of x. There could be a question where you're expected to know for yourself what substitution you're going to make, but with practice, that will become easier and easier to identify what to do each time there. So let's begin with this u. Before I substitute that in, we know at some point we're going to have to replace this dx, so we might as well get stuck in immediately and find the value of du by dx. So differentiating sine x, we know becomes cosine of x, and then if I wanted to have a look at my du, for example, du over cosine of x, if I divide there, is equivalent to d of x. Now, having a look at the fact I've got a cosine here, that looks like it's going to work out beautifully for me. And rearranging the u as well, so I kind of maybe should do that up here, u minus 1 is equal to sine of x. Okay, so I really think that I've got all the components that I need. That cosine of x and this cosine of x is going to cancel. This sine of x can be replaced by this sine of x. And I know that this 1 plus sine of x here is going to get replaced by this section here. So let's put all of this in. Right, so I'm going to have cosine of x times by sine of x there in the red. So I'm going to be substituting that for u minus 1. This 1 plus sine of x is obviously equivalent to u. So I'm going to replace in that for u cubed. And then my d of x over here, I'm going to replace in by this part here. So I'll get du over cosine of x, and there we see that our cosines of x's are going to cancel out. So that's going to leave us with, so u cubed outside of u minus 1, integrating with respect to x. So that's going to be u to the power of 4 minus u cubed. No, not integrating with respect to x, sorry, integrating with respect to u. So used to saying with respect to x. Okay, and that will work out quite easily for us. Increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power, plus c, because there are no limits. And all I simply need to do now is substitute back in for u, so that the final answer is in x, the same way that the question was originally. So remembering that u is 1 plus sine of x there. So I have 1 plus sine of x to the power of 5 over 5, take away 1 plus sine of x to the power of 4 over 4 plus c. Perfecto. Okay, so here we have a special case. That's another special case for you to learn, yep. And this is where we're going to use substitution of a trig function to help us solve a question. Yeah, you heard that right. We're going to be substituting with a trig function. Now, normally the idea of introducing a trig function to a question would make you feel like that's going to make the question 10 million times harder. But with this, it is actually the best way to solve this question. And it does then kind of become this sort of standard example that you'll be expected to know and be able to use competently. So let's get started. I've got here the square root of 1 minus x squared. Is this 1 minus x squared which makes using a trig function, or in this case a trig identity, really good to use? So I'm going to start by saying let x be equivalent to sine of theta. Okay, and if I do that, Inside of that square root now, I'll end up with 1 minus sine squared of theta. Interesting. Because if you go back to your identities, you will recall that sine squared of theta plus cosine squared of theta is equivalent to 1. So if I rearrange that slightly now, cosine squared of theta is equal to 1 minus sine squared of theta, which conveniently looks exactly like what I have inside the square root. So I'll get the square root of cosine squared theta. Beautiful. Let's move on. So if I continue with this sort of approach, once we've got x, it's usually, worthwhile investing in finding out what dx is, so differentiating. We know that differentiating the sine function makes it go to cosine, so I'll get here cosine of theta. So let's have a look there. That means that dx alone is going to be cosine theta d theta. Okay then. Popping that in then, we are going to get 1 over the square root of cosine squared theta. And then in place of our dx now, we're now going to have cosine theta d theta. So cosine theta d theta. Wonderful. Taking that denominator now, what's really cool about it is that I've got cosine squared and the square root. So if I actually take the square root of the squared function, I am going to get cosine of theta. Here I'm still multiplying by that cosine of theta d theta, and if my cosine theta became part of the numerator, well, they're going to cancel, aren't they? They're not going to cancel out completely to give me 0, okay? That's a common mistake at this point. They're going to cancel out to give me 1. So I'm going to integrate 1 with respect to theta. And that is going to give me theta, because obviously I'm integrating with respect to theta, plus c. Okay, interesting. Going back to the original part then, if I know that x, we said to let x be equal to sine of theta, in order for me to get the value of theta, I'd need to do sine to the minus 1 of x. Okay, and remember, when we're working in the second year, instead of saying sine to the minus 1, we do usually call that arcsine. So if you read that in a textbook, don't worry, you have done it and you do know what it is. So putting that in here, I shall get arcsine of x plus c. And that is the answer to the integral of 1 over the square root of 1 minus x squared. Bet at the start of this you never realised there was going to be a trig function for an answer. Nope, but then maths is awesome. Okay, so here is an example of where we are asked to integrate with limits. This is going to be a longer than normal question because we're going to be making substitutions for our x, for this x plus 1, for the dx, but then we are also going to need to remember that we are going to have to make some substitutions for our limits, and I'll explain why as we go through this. If you were given this question in an exam and you weren't given the substitution, it's usually whatever is kind of in the brackets that's the best to sort of go for. So I would say, for example, let u be equivalent to x plus 1. And let's see if that works for us in this example. So the first thing I'm going to see, I've got an x here. I just want to rewrite this in terms of x, so making x the subject of the formula so that I can substitute for that. So if I say u minus 1 is equal to x, then I have exactly that. I've got my substitution for x. Then I'm going to have a look at du by dx. So du by dx, because I'm going to need to integrate with respect to x if I'm putting with respect to u if I'm putting u into this function. So if I have a look at differentiating this, that's going to be 1. So I can see that du is equivalent to dx. Well, that is quite nice, isn't it, really? Last but not least though, unless at the end of this question you're going to work by substituting u back for this x plus 1 expression here, and you'll see why later why you might not want to bother doing that, we are going to need to address the limits. Okay, and make sure that if we are working with respect to u, so I have something u cubed, u times, or with respect to u, that those limits on the integral are also going to be in terms of u. So if I take this expression, u is equal to x plus 1, so at the moment I have the limit when x is equal to 2, so my limit for u is going to be 2 plus 1, which is 3. Okay, so that's that upper limit sorted. Then I've got the lower limit. So the lower limit is when x is equal to 0. So again, using that expression above, that would be u is equal to 0 plus 1, which is just 1. So now let's put in all of the little bits that we need to make this work. So I'm integrating between the limits of 3 and 1 rather than 2 and 0. Instead of the x function that I've got here, I've now got u minus 1, which I'm going to put in brackets because I know I'm going to be multiplying it by another function. So x plus 1 is u, it's got a power of 3 on there, so times all that by u cubed. And then we know that dx is equal to du, so I can just make that straight swap, which is lovely. So I'm integrating now between 3 and 1, u4, or u to the power of 4 minus u cubed with respect to u. So increase the power by 1, divide by the new power, increase the power by 1, divide by the new power. Do not write plus c on this one because in this example I have been given limits to evaluate. So I can just put those limits straight in now because those limits are for a u function and I have a function that is in terms of u. So I'm going to have 3 to the power of 5 over 5, subtract 3 to the power of 4 over 4, and then all of that I'm going to subtract. So 1 to the power of 5 is just 1, and 1 to the power of 4 is just 1. So that's what I will have there. Evaluating those, okay, so 3 to the power of 5, that's going to give me, so in that bracket there, 243 over 5, take away 81 over 4, and then here, sort of the fifth, take away the quarter is going to give me, I believe, the 20th. Now, it's really important, I feel, that you show at least up to here in the exam, and even if you are using your calculator to work out each part, I feel that this demonstrates your method, and it's really important that you don't just sort of stop here, put all of that into your calculator and write in the answer, especially if you're not very good at using your brackets and things. Just do it bit by bit, write it out in full so the person marking your work can see what you've got and where it's come from, and if there's any mistakes they can easily identify it. Putting it into your calculator at this point will spew out an answer of 28.4 when you write it as a decimal and not a top-heavy fraction. And that is your final answer. That's the area under the curve if I was working with you between 3 and 1. But that is also exactly the same as the area under the curve for this function between 0 and 2. And there we have it. Example over.